So direct calculation in Schrödinger theory for free particle so if overlap I free is nothing but xf e to the power minus I by h bar pf minus ti p hat square over twice m xi. So now what you can do is to write it as a momentum integral. So insert the momentum completeness relation, and then also simultaneously do the Euclideanization twice in h bar, then p xi. So if you do this, insert this momentum completeness, then this again is going to be in real time going to be a heavily oscillatory integral, because this will have this is the same thing to the power minus I by h I times tf minus ti times p square by twice m for large p, p both for positive and negative, that is highly oscillatory, and therefore it is the same problem, and we are Euclidean analytically continuing. And these, after using the result for the xp overlap, is this comes out to be 1/2 pi h bar integral dp minus infinity to plus infinity e to the power I by h bar p times xf minus xi minus uf minus ui divided by twice m h bar times p square. And this is a Gaussian integral which can be performed by completing the square and so on, and the result is given by square root of, I'm giving directly the result of the square root of m divided by 2 pi I h bar pf minus ti e to the power I by h bar m by 2 xf minus xi square divided by tf minus ti. And this is nothing but e to the power I by h bar is free this same object here, this one, right? I by h bar m by 2 times that, right? So therefore, the rest of the factor must be c times f0 by definition. So this is therefore c times f0 is this is the c times f0. Therefore, for harmonic oscillator, for harmonic oscillator, one has if I equals e to the power I by h bar is harmonic oscillator of x lower bar, the classical phase, times so you just substitute this result into in here, square root of omega t minus by sine omega t and the final result is written in this way: m omega divided by 2 pi I h bar sine omega tf minus ti. You can do a long calculation. I'm going to give you the result, not the details of the calculations, but so it's an exercise. Show that S harmonic oscillator X lower bar, which X lower bar satisfies that initial and final condition, is given by m omega divided by 2 sine omega t times xi square plus xf square cosine omega t minus 2 xi xf, where t is equal to tf minus ti. It's a straightforward calculation, but a bit lengthy calculation, but I think it's worth doing once. And so if you substitute this result back in here, then you get the current propagator for the harmonic oscillator. Okay, so that's about it for today's lecture.